Work. Work has the ability to increase or decrease the amount of energy at a certain position in time and space and to change the motion of objects. Work has the same unit as energy, joules. What is work? It is not what is talked about in common language. It is unfortunate that sometimes physics uses words that are used every day in a quite different fashion. For example, if you're holding up a heavy box, do you think you're doing work? You're not. Work, in physics terms, is defined as the exertion of a force over a displacement where only the component of the force in the direction of the motion is relevant. For now, we'll assume a constant force. If you're just holding a box, you are certainly exerting an upward force on the box to keep gravity from pulling it to the ground, but it's not moving, so there is no displacement, therefore there is no work. Our equation is right here. Delta E is the change in energy. This is work. F with this little symbol here, that's the force parallel to the displacement. D will be our displacement. And then cosine theta is the angle between the force and the displacement. So over here, we got rid of the parallel sign here. That's what cosine theta takes care of. A common statement that energy is the ability to do work, that's not always the case. Energy needs to be concentrated to perform work on objects. Let's take an example. Strong winds, fueled by large amounts of energy in the air, can move windmill blades by applying a force to the blades. The windmill blades can then turn a set of grinding blades that perform work on wheat to turn the kernels into flour. The blades are doing work on the kernels. But if the energy of the air is dispersed over a great area, the winds are not focused enough to spin the windmill blades, so no work is done by the air on the blades. But the energy in the air is still there. It's just not concentrated enough. The work units, we've already said it's joules, but let's see where that comes from. Here's our equation, and of course this is joules, right? Change in energy. But let's look at the force. That's measured in newtons, and distance is measured in meters. So the unit of work is the Newton meter. And since a Newton is a kilogram meters per second squared, 1 Newton meter equals 1 kilogram meter squared per second squared. In honor of James Joule, who made critical contributions in developing the idea of energy, the unit of work and energy is also known as the joule. So the joule is 1 Newton meter, which equals 1 kilogram meter squared per second squared. And this is how it's abbreviated. 1 joule is 1 Newton meter equals 1 kilogram meter squared per second squared, and we'll just go ahead and use joules. Joule was instrumental in showing that different forms of energy can be converted into other forms, such as thermal to mechanical energy. Before Joule, it was commonly accepted that thermal energy is conserved. This was disproved by Joule's extremely accurate and precise measurements showing how thermal energy is just another form of energy. This was made possible by his experience as a brewer, which relied on very accurate measurements of temperature, time, and volume. Consider a system composed of one block. When a force acts in the same direction as the block's motion, then the work done is positive and the energy of the system increases. If the force acts in the opposite direction as the block's motion, then the work done is negative and the energy of the system decreases. If the object does not move, then zero work is done. Work is a scalar. It has magnitude but not direction. The unit of work is the joule, just like energy. Here's a good way to visualize it. When an object moves in the same direction as the direction of the force, so here's our force, and we're saying the object is moving this way, our force and displacement are in the same direction, the work is positive, the work is greater than zero, and the energy of the system increases. Acceleration occurs due to the unbalanced force. Well, there's only one force, and it's to the right. When the object moves in a direction opposite direction of the force and displacement are in opposite directions, then the work is negative. The energy of the system decreases. So how does this happen? Well, picture this as a car, and it's moving in this direction, and you hit the brakes. The acceleration and the force are certainly in this direction. Remember, the force doesn't tell you which way you're going, it just tells you what the acceleration is. So the car is slowing down, so its energy decreases. If the object moves in a direction perpendicular to the direction of the force, that means the force and there's a couple of forces here, and the displacement are at right angles, then the work is zero. The energy of the system is unchanged. No acceleration occurs, either in this direction or that direction, since no component of force acts in the direction of displacement. Therefore, no work is done by the normal force or the force of gravity, as they are perpendicular to the displacement. But what if, instead of pulling the object horizontally, what if it is pulled at an angle to the horizontal? This has been done before in dynamics, and we're going to do it again. Resolve the applied force into components that are parallel and perpendicular to the direction of motion. No work is done by the perpendicular component. Work is only done by the parallel component. So using a little trig, F parallel is equal to the applied force times the cosine of this angle here, theta. So one of the equations we started off with was this, and actually F parallel was represented by this. But we can make that look a little cleaner because we only need this here, the applied force times cosine theta times d. Then we move d in front just so it doesn't get confused with the cosine. The work done on an object by a force is the product of the magnitude of the force and the magnitude of the displacement times the cosine of the angle between them. Instead of pulling the object at an angle to the horizontal, what if it is pushed at an angle theta with the horizontal? And again, we did this in dynamics. This is really no more difficult a case. Find the component of force that is parallel to the object's displacement. The interpretation is the same. Just determine the angle between the force and displacement and use work equals F applied times d cosine theta. The angle theta that F app makes with the horizontal is the same as the angle that the extended force makes with the horizontal, as shown by the vertical angles theorem. So these two angles are the same. Even though F perpendicular is in the negative direction, it was positive when the object was pulled in that direction, it does not affect the work, as only the parallel component contributes to the work. Many physics problems require the use of vectors. Most of the solutions in this course so far have involved the sum and difference of vectors using trigonometry to add and subtract vectors that are at angles to each other. Multiplying vectors by scalars has also been used. Calculating work involves the multiplication of vectors, but a special kind of multiplication. There are two types of vector multiplication. One results in a scalar quantity, like work, and that's the vector dot product, and the other a vector quantity, the vector cross product. Work uses a scalar dot product. Frequently, the word vector is dropped. The process for multiplying vectors is covered in AP Physics C. The dot product is introduced on the next slide to show its elegance, but it is not required knowledge for AP Physics 1, and the next few slides may be skipped if you would rather wait for AP Physics C. The vector cross product is a little more advanced and will not be shown. The scalar dot product is defined as vector A dot vector B is the magnitude of vector A. The magnitude of vector B doesn't mean absolute value here, it means magnitude, times the cosine of the angle between them. The dot product multiplies the magnitude of the component of vector A, so here's vector A, here's A cosine theta, that is parallel to vector B, and the magnitude of vector B. It is also called a projection of vector A on B. For example, if you had light coming down here, and this were, a rod, a ladder, it would throw a shadow that had a length of A cosine theta. The value of the dot product can be positive, 0, or negative, depending on angle theta. Theta ranges from 0 degrees, let's say our A is right down here, and then you can keep increasing angle theta until you go in the totally opposite direction. Theta ranges from 0 to 180 degrees. The dot product is a maximum positive number when the two vectors are in line. That's when theta is equal to 0. And a maximum negative number when the two vectors are anti-parallel. That's when theta is equal to 180 degrees. It is equal to 0 when theta is equal to 90 because it's perpendicular. Let's apply this to work now. we've got our general formula for dot products. We've also shown that work done by a force at an angle to the displacement is the magnitude of the applied force times the displacement times cosine theta. So let's replace A with FAP in our equation here, and B with D, and we get work is the applied force dot D, and both of those on the right side are vectors, and work is a scalar. Time for some example problems. A 60 Newton force is applied to an object that moves 15 meters in the same direction during the time that the force is applied. How much work is done to the object? This is a one-dimensional problem, so we just need to use F is equal to Fd because the force and the displacement are in the same direction. We have our givens. We simply multiply them together, and we get 900 joules. Example 2. A 50 Newton force is applied to an object that moves 10 meters in the opposite direction of the force during the time that the force is applied. How much work is done to the object? Once again, we're not using the full work formula, but we're going to say the force is negative this time because it's opposite the motion. So work is Fd. Here's our negative 50 newtons, 10 meters. We're doing negative work this time, negative 500 joules. A force does 30,000 joules of work along a positive displacement of 12 meters. Find the applied force. The positive displacement is represented by plus 12 meters, and since we're doing positive work, that has to be in the same direction. So we take our work equation, again, not the two-dimensional version, we divide both sides by d, and we substitute in our values, and we get 2,500 newtons. How high can a 40 Newton force move a load when 400 joules of work is done? Once again, we have a one-dimensional problem, so we start with work is Fd, solve it for d, plug in our numbers, and we get a height of 10 meters. Now we have a two-dimensional problem. We have a 50 Newton force pulling an object at an angle of 53 degrees to its direction of motion. Its displacement is 6 meters. How much work is done by the force on the object? We now have a two-dimensional problem, so we use our full equation here. We plug in the values, force, d, and the cosine of 53 degrees, and we get 181 joules. There's another way to do this without using your calculator. If we recognize here, this is 53 degrees, which means this over here is 37 degrees. That is the famous 3, 4, 5 right triangle. So if we wanted to not use our calculator, now this is approximate, right? It's not exactly 53 degrees for our 3, 4, 5 triangle, but it's close enough. So I'll have 50 newtons times 6 meters times the cosine of our angle, which is going to be 3 over 5, adjacent over hypotenuse. So 5 into 50 goes 10, 10 times 6 is 60, 60 times 3 is 180.